Welcome to the second lecture of the course Statistical Data Analysis 2. In this lecture, let's first talk and think about model parameters. So, if you remember, last week we looked at different kinds of data and how we might want to model them statistically. At the core of statistics, regardless of whether we are doing a hypothesis test or if we are trying to understand the generative process that produced some data, we always want to estimate certain parameters. Let me give you an example. Let's say we have the situation again that we have a data set with two variables, x and y, that are both continuous. Last week we saw psychological symptoms and the stress level, for example. And so these data are scattered somehow. I'm plotting the x and the y value for each data point, for each subject, like participant in a study maybe. And so we saw last time the idea that we might want to make the assumption, like we might want to postulate a certain model of these data, in this case a simple linear regression model, and then find the best parameters of that model that explain these data. So let me just recap what that means in this context. So we saw this formula last time, right? So y is equal to alpha, which is the intercept, plus beta x I, because that's always for an index for the specific data points, plus some residual variance that we will just call epsilon here. And now the interesting unknowns here are, of course, alpha and beta, the intercept and the slope. These are the parameters of this linear regression model that we want to estimate. And once we found the optimal values for the parameters alpha and beta, remember from last time, those that minimize the sum of squared residuals, you could say, then we can represent them as the best fitting line for these data, right? So this pink line here now represents our specific linear model that explains our data best. So the core idea is that we make this assumption beforehand that there will be some kind of linear relationship. So that's already a constraint of this model. It can't find a more curvy shaped line, okay? There are other models that can do this, but this simple linear regression model says, okay, we have these two variables and we're assuming a priori that they are somehow linearly correlated. So the relationship could be like this, or it could be steep like this, or it could be descending like that. But it turns out that once we find the optimal alpha and beta for these particular data, we might have this like slightly ascending line. So the bottom line is the model, like the structure of the model, for example, a linear model tells us what kind of relationship we're expecting a priori, in that case, a linear relationship. And then the process of fitting the parameters of the model is like finding the optimal way under the assumption of the model. For example, we have a linear relationship to explain these data. So in this case, with a specific value for alpha the intercept and beta the slope that minimize the residuals. Okay, so this was an example of a linear regression model and its parameters, namely the intercept and the slope. Okay, so now let's look at a different situation. Let's say we have a data set, only one variable, a continuous variable. We can again call it y. And let's maybe show the histogram of this variable. So maybe it looks somewhat like this. So there might be some irregularities here. It's a sample of data, okay? But let's say it looks roughly like that. It could be, for example, I don't know, what examples that we have, IQ scores or any other kind of measure you can think of, like body height or something, okay? And so this is now the distribution in a particular sample from some population. And now we might have the idea in mind, the model of these data in mind, which is that this is a Gaussian process. In other words, these data are generated from a normal distribution, like normal distribution, Gaussian, that's kind of synonymous. So we might say that our model of these data is the following. So y, which is our variable of interest here, is sampled from a normal distribution with a particular mean mu and a particular standard deviation sigma. Okay, where, as you surely remember, mu represents the central tendency of these data and sigma represents how wide the spread is. Now, we saw here we had two Greek letters, alpha and beta, that were our parameters that had to be estimated. And likewise here we have two Greek letters, so we see a pattern here. And these, in this case, for the Gaussian process, are our parameters that we want to find. Because you can imagine that there are many possible normal distributions with many possible values for mu and sigma, each of which would look a bit different. So if we, maybe I'll add another coordinate system here. So if we imagine that this is our axis for the variable y, then there are all sorts of normal distributions that we could have. So we could have a normal distribution where mu is here maybe, so the central tendency is here and then it looks like this, but we could also have one where mu is here and the sigma is much larger, so it might look like this. And we could also have one where maybe mu is here and it's very tight, so it's maybe like this, and many more. Like we can have many possible different normal distributions, infinitely many of them. I can't draw all of them here. And we want to find the one and only that most optimally describes or imitates these data. Because again, we are assuming that these data came from one of those, and we just have to find the one which they came from. That's the idea. And how do we find the one which they came from? Well, we have to find the optimal parameter values mu and sigma that will tell us which it came from. So once I found the optimal mu and sigma, I might as well draw the normal distribution that they represent here. Might look somewhat like this maybe. And so here we'd conclude that this empirical data, this sample, which is represented by this histogram here, most likely came from the normal distribution with these two parameter values that represent this particular normal distribution out of all the possible ones. So that's what we would do for data that we assume to come from a Gaussian data generation process. So in general, regardless of the particular statistical model that we are looking at, whether it is a linear regression model that tries to explain the relationship between two variables, or whether it is a Gaussian process model that is a normal distribution, which tries to explain how one variable is generated, like data from one particular continuous variable. The thing that is common to all statistical models, and even to the much more complex ones that we're going to see throughout this course, is this general idea of saying, look, we are assuming some kind of model structure, so what we will find is not totally arbitrary. For example, we have in mind as the structure of a model that explains this relationship that it should be a linear relationship, or we could have in mind as the structure of the model that will explain the distribution, the generation process of this variable, that it is a normal distribution, like it's a normally distributed variable. Like we will bake this constraint in from the beginning, and then what is left to do is to find the particular parameters within, for example, the general structure of a linear model or the general structure of a Gaussian process, which will constrain the model even further to optimally match the data that we have at hand, with the idea in mind that this will be our best guess of trying to explain these data. Like once we've found the particular Gaussian process with the particular parameters mu and sigma that looks most like our data, we might say, okay, this is our best guess of finding the true generative process behind these data. Like we don't know for sure, of course, but if we have to to make a guess, we'd say, well, it's maybe the process with mu equals 611 and sigma equals 100. Likewise, here we would say, okay, so our best guess, given the assumption that there is some kind of linear relationship after fitting the optimal line, is that the relationship between stress level and psychological symptoms is best explained by a linear model with intercept, I don't know, 10 and slope 0.5 or something like that. And so the real tricky problem that we are faced with every time we are dealing with statistical models is how to find the optimal parameter values given a sample of empirical data. Like, for example, how to find the optimal values for alpha and beta in a linear regression, or how to find the optimal values for mu and sigma in a Gaussian model. And so we've seen some ad hoc solutions, like some specific cases of how to do that, which work very well. For example, for linear regression, we saw that what we have to aim for is to minimize the sum of squared residuals. So we could actually just solve this analytically using calculus. That should not be very hard. Or in the case of the Gaussian process, which is assumed to generate our data from this one single variable here, we could just compute the sample mean and compute the sample standard deviation, as you've learned in the previous stats course. And we know as a fact that these are actually estimates of the true mean and the true standard deviation in the population. So these are also, in a sense, like our best guess. So these are strategies we could use for these two particular model types. So doing this least squares regression for the linear regression model, or for the Gaussian process, computing these sample-derived estimates like the sample mean and the sample standard deviation and just plugging them in as like plausible values for our real population parameters. But there is also a much more general way and much more powerful way to find the optimal values for parameters in a statistical model. And this way will work for any kind of model we might deal with in the context of frequentist statistics, even more complex models than these two here. And this method of determining the optimal value for model parameters is called maximum likelihood estimation. And understanding how maximum likelihood estimation works will be key to understand one of the most powerful statistical tests, or like flexible statistical tests, that we will encounter in the context of this course, namely the likelihood ratio test. So as you might notice, the term here on the right, maximum likelihood estimation, contains the word likelihood. So what is a likelihood? So the likelihood. In order to understand what a likelihood is, it would be best to start from a concept that we sure all remember very well, namely a probability density function. A probability density function is a function that is continuous and whose area sums up to 1 overall. A very well-known example that we have worked with a lot in statistics so far is the normal distribution function. So let me just spell it out as an example. Like if we are looking at the normal distribution or Gaussian, which is just a synonym, then our function could be defined as follows. The function would be f of some data point y with index I, provided some values for the parameters mu and sigma, equals to 1 divided by sigma times the square root of 2 pi times e to the power of minus 1/2 times the square of yi minus mu divided by sigma. So this function gives us the probability density for the observation of a particular single data point yi. And an interesting question is if we can describe a similar function, but more generally, in the sense that it can provide the probability density for the observation of an entire range of data points that we may call y1 until yn. For example, the data observed in a particular sample in an empirical setting. So that's what we want to do. We want to find a so-called joint probability density function, which will describe the joint probability density of observing all data points y1 until yn in a particular sample. And let's see how its formula will look like. So in order to acquire our joint probability density function, the thing we have to do is the following. We just compute the probability density as we know it for each individual of these data points, and then we take the product of all resulting probability densities. That will give us the joint probability density of observing all of these data points together. That is assuming, that's a crucial assumption we have to make here, that these data points are identically and independently distributed. If they aren't, then this would be a wrong way to compute the probability density. But for all our purposes, where we like randomly sample from a population, that is in fact the assumption we have to make, right? That we have independently sampled these data. So representing this mathematically, I could write that I have a function f which takes a sample of n data points, y1 to yn, and is also provided some values for our parameters mu and sigma. And then this joint probability density is just computed, as I just said, as the product, that's what the capital pi stands for here, iterating from y equals 1 up to n of, well, this probability density as we had already defined it here, but now each time reevaluated for each of these data points. So just spelling it out again quickly, 1 divided by sigma times the square root of 2 pi times e to the power of 1 minus 1/2 times yi minus mu divided by sigma squared. And simplifying this term a little bit, we could actually rewrite it as follows. We could say this is equal to 1 divided by sigma times square root of 2 pi to the power of n times e to the power of minus 1/2, the sum ranging from 1 to n of yi minus mu divided by sigma squared. So in a way you could say that this joint probability density function is asking how probable is it to observe my sample. For example, let's say I've computed the psychological symptom score from some range of students, and I got different values, like so let's say I've examined 30 of them and the values are maybe 10 and 5 and 11 and 17, right? I have 13 of these numbers. These are my data points y1 up to yn. And so if I plug this into this function and I assume that these psychological symptom scores come from a specific normal distribution with mu and sigma, then the joint probability density that basically describes in a way how probable it is to observe these data points would be represented by this function. And the crucial thing with the likelihood is that here we are basically flipping around the question. So here we have the joint probability density function, which is a function which takes as its argument, as its primary argument, the data, and it considers given a certain hypothesis, where the hypothesis is the specific value for mu and sigma that we have provided. And the likelihood has the same function term, like it's also a function, but we now ask the opposite question. So we basically say now we have a function which we will call capital L of the parameters mu and sigma, given or provided some data y1 to yn, okay? So now we're asking a different question. So we are basically, even though like the function term still looks exactly the same, it is now about how likely our parameters mu and sigma are given some specific data, okay? And that is the likelihood. That is the likelihood function. So here we would now maybe also relabel this here, and this will be our likelihood. So the likelihood function is a function that takes two arguments, because we have two parameters, right? We have mu, the mean, and sigma, the standard deviation. Well, that's at least for our normal or Gaussian example that we are looking at here. And the data obviously also go into the function, but they are supposed to be given, so they don't really count as an argument. The real two arguments that we're interested in for the likelihood formulation of this function is how mu and sigma vary and how that affects the output, okay? And so we could imagine to draw this function as follows. This will be a drawing of a so-called parameter space. So we have two inputs, so that is mu and sigma. And then the outcome, well, I would need a third dimension here. I could draw it maybe like this. This would be the axis that describes the likelihood given some values mu and sigma. But maybe let me draw it differently. So you just have to imagine that there's a third dimension that is basically pointing towards you, going outside of the screen, okay? But anyway, maybe somewhere in this parameter space, like we have like many possible different points here. And so each point represents a possible combination of a particular value for mu and a particular value for sigma. And let's say somewhere in the space, there is the optimal combination of mu and sigma in such a way that it maximizes the likelihood, like the resulting value from this calculation. So let's say this is maybe the sweet spot. So this is the optimal combination for mu and sigma, the so-called maximum likelihood estimate, or MLE. And that's like the peak. If we imagine that this is like a mountain going out of the screen basically towards you, this is the peak of the mountain. Then maybe around it we have like also an area where there are values that are like at least likelihood of something, and then maybe going further, like you would visualize maybe how you would draw the terrain of a mountain, okay? I'm drawing something like this now. So you could imagine that it is a mountain that has like this shape, and like at this one particular point here we have the maximum likelihood estimate because this particular optimal combination of mu and sigma values gives us the highest likelihood as computed by the formula to the left. And as you may guess, the goal of maximum likelihood estimation is always to find the maximum likelihood estimate. So that is what we want to do. Now, in order to work with likelihood functions, it is often easier to actually log transform them first, because that will make a few mathematical operations that we will have to do more tractable. So we will have a look at how to log transform the likelihood function, and this will give us the log likelihood function. So the log likelihood can be given as follows. Instead of writing capital L, we will now write small caps L. Okay, so that's the conventional symbol, and it's going to be this curly kind of lower caps L. The arguments are exactly the same as for the original likelihood function. So we take mu and we take sigma, and then we are given some data from y1 to yn, okay? And as I said, basically the log likelihood is nothing else than taking the logarithm of the original likelihood function. So that is, I'm going to spell this out once explicitly. So we're taking the natural logarithm, that is the logarithm with respect to base e, of the original likelihood function term. So basically the natural logarithm of whatever capital L of mu and sigma given the data was. And once we evaluate this in detail, mathematically, what we will end up with is the following log likelihood function for our Gaussian case here, namely the term minus n divided by 2 times the natural logarithm of 2 pi times sigma squared minus 1/2 times the sum ranging from I equals 1 to n of yi minus mu divided by sigma squared. Now, the nice thing about the log likelihood function is that, well, it is mathematically a lot more tractable than the original likelihood function, because everything that is a product, like a multiplication, on the normal number scale becomes a sum in the log scale. And summing things, especially when we get to more complicated likelihood functions, is computationally much easier for us to do than to multiply things, okay? So that's why we usually in practice want to work with a log likelihood function. And why can we do this? Like, why can we just use the log likelihood function in order to do maximum likelihood estimation? Well, because the second nice property of the log likelihood function is that whatever its maximum is, it will be exactly at the same place in this parameter space as for the original likelihood. So like the property of like which likelihood value is the highest, that will be exactly preserved in the log likelihood function in the same way that it was for the likelihood. So we could draw this exact same shape of our mountain where we are searching the optimal parameter combination of mu and sigma, which is our maximum likelihood estimate. And regardless of whether we are looking at likelihoods or at log likelihoods, the optimal pair of mu and sigma values will be exactly the same. That's why we can use the log likelihood safely. Now, the question you may be asking at this point is, well, how do we find the maximum likelihood estimate? Conceptually, we can go about this as follows. If you remember maybe from the last time you had classes on calculus, there is a certain way in general in math how to find the extreme points of a function. So the extreme points could be either a maximum or a minimum. And here what we want to find is the maximum of this likelihood, or well, of the log likelihood function, which shouldn't make a difference. And if you remember from calculus, there is a certain procedure we can apply, namely to take the derivative of the function, like to differentiate it, and then set the derivative to be equal to 0, because, well, at an extreme point, the rate of change of a function is 0, and then solve this equation with the derivative set to 0 for our particular variable we are interested in. And that's exactly what we can do here. And here, because we have a multi-variable function, like we have two inputs, mu and sigma, we actually need to take the partial derivative with respect to each of these two arguments. So we could write partial derivative of the log likelihood function, for example, with respect to mu, and we'll set that to 0. And then we'll ask at what value of mu this is the case, like this equality is fulfilled, that the derivative is equal to 0. And well, it turns out that once we solve for mu, like once we find the particular mu that satisfies this, this will be our maximum likelihood estimate from mu, because that's the mu that is located where the likelihood is at maximum. And similarly, we can do the partial derivative with regard to sigma, do the same thing, set it to 0, ask at what sigma is this equality satisfied, and answering this question will give us sigma hat, like mu hat and sigma hat, that always represents the estimates, in this case the maximum likelihood estimates for our real parameters mu and sigma. And so this is how we can find our maximum likelihood estimates for mu and sigma using maximum likelihood estimation. Now there are a few caveats. So we can do this in the Gaussian case safely because there's only one extreme point for a Gaussian likelihood function, and the extreme point is always the maximum. So once we have done this, we're okay, and we can immediately conclude that these two are our maximum likelihood estimates. But there are other functions that might have like a more mountains and valleys kind of shape, like different likelihood functions, where there are multiple extreme points, and maybe some of them are actually not maxima but minima. And obviously we don't want to consider the places where the likelihood is at minimum, but only where the likelihood is at maximum. So in other cases, for more complex likelihood functions, not for the normal or Gaussian one, we would have to do a few further checks to really make sure that these points that we found are in fact maxima, and also maybe if there are multiple of these extreme points, which one is really the global maximum of the likelihood function. So it gets a bit more tricky in other cases, but for the Gaussian case, there's only one extreme point. It's always the maximum. So just checking where the partial derivative is equal to 0 is perfectly sufficient to find our maximum likelihood estimates for the mean mu and the standard deviation sigma here. The next thing we're going to see is how to use maximum likelihood estimates and, well, the accompanying likelihood value for the particular maximum likelihood estimate in order to test specific hypotheses about our parameters, okay? And this sort of testing using these likelihoods from the maximum likelihood estimates is referred to as the likelihood ratio test. And so what this would mean typically is that we may want to ask a question about some parameter, for example mu in our Gaussian process model. And the question we might ask, so the hypothesis we want to test could be, is mu actually different from 0, okay? And what we would have to do in order to tackle this question is to compute the likelihood, or let's say the log likelihood, which is usually a bit easier. So the log likelihood of 0, so mu set to 0 and sigma, and also compute the likelihood, or well, the log likelihood of our maximum likelihood estimate, which is mu hat. And then we want to compare these two, okay? And so the general intuition is that whichever has a higher likelihood, like whichever value for mu, whether it's 0 or whether it's the maximum likelihood estimate, that is the one that is more likely to be the case. And well, kind of by definition, the maximum likelihood estimate will always give us a likelihood value or a log likelihood value that is larger than the likelihood value where we set mu to 0, for example, well, unless the maximum likelihood estimate is 0 itself. But the crucial idea is this difference big enough? So is this a meaningful difference? Is this a significant increase in likelihood? Okay, going from the likelihood that the null hypothesis value for the parameter might have, so null hypothesis might say that mu is equal to 0, our maximum likelihood estimate says mu is equal to mu hat, and we want to test basically statistically if going from this likelihood to that one leads to a significant increase in likelihood. If it does, then we will conclude that we can reject the null hypothesis, and our new best guess for what the real mu is behind our data will be our maximum likelihood estimate. But if this is just a small difference, so, well, the likelihood for the maximum likelihood estimate is a bit bigger, obviously, than the one for the null hypothesis, but maybe not big enough. In that case, we would say, well, we can't really know for sure. Maybe our null hypothesis that mu is 0 is still correct after all, okay? And the interesting and crucial aspect of this is how to determine if the increase in likelihood or in log likelihood here is meaningful, is significant or not. And how to do this is the core of the likelihood ratio test, which we're going to look at next. All right, so more generally speaking, we could say that we have a null hypothesis about some particular parameter. Let's just generally call it theta as a placeholder. And the null hypothesis says that this parameter theta has some particular value theta 0. For example, what we just had on the board was that we were testing the parameter mu in a Gaussian process model, and the null hypothesis would say that mu is equal to mu 0, and in our example this could be, let's say, 0 specifically. So we are testing if the mean of some Gaussian process is 0 or not. And the alternative hypothesis, H1, would say that theta is in fact different from theta 0, and that it is actually equal to the maximum likelihood estimate theta hat that we acquired. Okay? And so thinking specifically again of means mu in a Gaussian process model, we would say mu, or like the maximum likelihood estimate mu hat is equal to mu, and this is in fact not equal to mu 0, which was 0. And also in a concrete example, we could have that the maximum likelihood estimate itself is actually some specific number, like 53.14, okay? That would be an example. Now, with this general idea in mind, we want to use the likelihood ratio test in order to determine if we can reject this null hypothesis or if we have to retain it because there is no strong evidence to reject it. And that's what we're going to see now. The key concept in the likelihood ratio test is, as the name kind of suggests, the likelihood ratio. Okay? So what is the likelihood ratio? A likelihood ratio is, as trivially as the name might suggest, just a ratio between two different likelihoods. Which likelihood specifically? Well, we want to take the likelihood that represents our null hypothesis and the likelihood that represents our alternative hypothesis. So we're gonna write likelihood ratio with this capital lambda symbol, that's the convention. And this will be equal to the likelihood function evaluated where theta is set to theta 0, okay? Divided by the likelihood function result where theta is set to equal the maximum likelihood estimate, theta hat. And just as you can write the likelihood ratio, lambda, like capital lambda, you can also write the log likelihood ratio, like the logarithm of the likelihood ratio. And this will be equal to what exactly? Well, according to the rules of the logarithm, we can now just write this as log likelihood where theta is equal to theta 0. And now instead of dividing, we can subtract. So minus the log likelihood of where theta is equal to the maximum likelihood estimate theta hat. Okay? And from here, we are just one step away to obtain the test statistic that we will need in order to run the likelihood ratio test. And that is to compute -2 times the log likelihood ratio. Why is that the case? Well, because -2 times the log likelihood ratio turns out to be converging as a chi-squared distribution, where the parameter of the chi-square distribution k would be set to 1 in this case, where it's always the number of parameters that are fixed in the null hypothesis as opposed to the alternative hypothesis. And so this is nice because the chi-square distribution is a probability distribution which we can now use in order to run a hypothesis test, kind of like we use the t-distribution to run a hypothesis test in the t-test, or how we use the normal distribution, like the sampling distribution of the mean, to run a hypothesis test for the z-test. So here the analogous distribution that we need is this chi-square distribution, and the crucial idea is that if this null hypothesis is true, then this -2 times log likelihood ratio should be approximately looking like a chi-square distribution with the k parameter set to whatever the number of parameters that are different between the hypotheses is. So to clarify this a little bit further, obviously -2 times log of the likelihood ratio is just a single value, okay? So this is not a distribution, so you might wonder, what does it mean that this looks like a distribution? Well, this is under the idea that we are repeatedly sampling data and we are recomputing the log likelihood ratio and then taking it times -2. If we would do this repeatedly and repeatedly, then the overall distribution of these values that we get, that will look like a chi-square distribution. So this is the general idea. And now coming back to the specific example that we were talking about, namely the model that describes a Gaussian process, that could be now specifically defined as follows. So we want to define this statistic -2 times the log likelihood ratio. So this would be given by the following equation. So -2 times the log likelihood ratio. And in this specific case, like the Gaussian process, this will be equal to mu hat, that is our maximum likelihood estimate for the mean, minus mu 0, that is what the null hypothesis supposes mu to be, divided by sigma, the population standard deviation, divided by the square root of the sample size n, and then this whole thing to the power of 2, like the square of this entire term. This is the specific way to compute this test statistic -2 times the log likelihood ratio in the case of the Gaussian process, like if we want to test the mu parameter, the mean parameter for the Gaussian model. That's what we can directly plug in. For details, like how to derive this particular term, you can see the lecture notes there. You will be guided through step by step if you want to understand where this comes from. But for us, we can also just assume that we can use this term as a instant plug-in replacement for the pseudo chi-square test statistic of the likelihood ratio test when we're dealing with the Gaussian process. And another shortcut we can use in calculations with the model of a Gaussian process is that the maximum likelihood estimate of mu, which we have called mu hat, is actually always equal to the sample mean, x bar, okay? So that's an interesting property we can kind of take for granted because we already know it, even though we will not go over the mathematical proof of why that's the case. But long story short, when we have a sample of data and we would take its sample mean, then this will be equal to what we would also get using the bare bones method of maximum likelihood estimation. So we can kind of always assume for Gaussian processes that the maximum likelihood estimate will be equal to our sample mean, and that's what we could directly plug in here. By the way, note that this is just the same term that we use to compute a t-value for a t-test, only that here it is squared, right? So that's an easy way to remember it. All right, so I guess it might be time to see how we can use all these concepts just introduced, like the maximum likelihood estimate, the log likelihood ratio, and so on, directly in R in a simulated toy example. and see how we can conduct like a likelihood ratio test on it. So let's do that and open up our studio. There it is. So the first thing we might want to do now is to generate ourselves some like simulated data. Okay, so let's say we have some data which we will store in a vector called y, which comes from a normal distribution, and we generate 10 data points. Now, if we don't specify anything else, like if we don't specify the mean and the standard deviation explicitly, R will just assume that we want to sample from a standard normal distribution, that is a normal distribution with mean 0 and standard deviation 1. Okay, so let's do that. We can look at our data if we want, so let's visualize them. There they are, these are our data points. And the first thing we might want to do is we might look at this and think about, okay, what is the hypothesis, what is the null hypothesis, and what does it say about our parameter mu? So let's say our null hypothesis regarding these data, so we just received these data, we don't know where they came from, so just forget that we know how we simulated them. Suppose this is like our real experimental data, they just came delivered to us, we don't know where they come from, and we have the null hypothesis, which says that the mean of the population which generated these data, like the process which generated this data, which we assume to be a normal process, normal distribution, the mean of that should be 0. That is our null hypothesis. It says mu is 0, therefore like mu 0, which is like mu according to the null hypothesis equals 0, right? Now, that's basically this situation right here. And our alternative hypothesis would say that mu is actually equal to the maximum likelihood estimate. So mu hat is basically what our alternative hypothesis thinks that mu is. And the maximum likelihood estimate in a Gaussian process is, as we just discussed, like if we want to get it quickly in a quick and dirty way, as opposed to like doing the meticulous bare bones maximum likelihood estimation using differentiation and so on, we can just conveniently use the mathematical fact here that the maximum likelihood estimate for the mean of a Gaussian process is just the sample mean. Okay, so let's compute the sample mean, and we can see what it is. So the sample mean here happens to be 0.07. Okay. The interesting next step is now how to compute the likelihood of these data that we sampled, either under the assumption that the null hypothesis is true or under the assumption that the alternative hypothesis is correct. So let's start with the likelihood under the assumption that the null is correct. So in this case, let's call it capital L, H0, like likelihood under the null hypothesis. And as you remember from what we discussed earlier in this lecture, we can compute the likelihood just as the product of the output of the probability density function evaluated on each of these individual data points in our sample. Okay, and we can do this quite conveniently in R by writing product that will just compute a product of whatever vector we give this function, and we want to have the product of dnorm, which is just our language for probability density function for the normal distribution. Of what exactly? Of our data y, specifically of each of the data points in y individually, under the assumption that the mean of this probability density function for the normal distribution should be at, well, here it is, mu 0, which is 0. So let's write mu 0. And we can compute that, and we can also see what the likelihood is in this case. So the likelihood turns out to be this particular number, which is very, very small, very close to 0. Okay. We can also compute the log likelihood, as we know that is also quite easy. So let's maybe write the log likelihood as small caps L. So small caps L for H0. That will be, well, thanks to the properties of the logarithm, will not be a product now, but a sum of certain things. So it will be the sum of what exactly? Well, of the logarithm, the natural logarithm specifically, of these individual outputs from the probability density function. So here inside this we would again write d norm, and then we would write y, and mean is equal to mu 0. And once we evaluate this, we get the log likelihood, which is the following value. And as you might already have thought to yourself, we could have also gotten it even quicker because we had already computed the likelihood. So we might as well just say logarithm of the original likelihood. This should give us the same output as we see here. All right, now we can do just the same thing, but for the alternative hypothesis, now assuming that the true parameter value is actually our maximum likelihood estimate. So in that case, maybe let's just reuse this code, but change it a little bit. So we're now going to say we want to have the likelihood under the alternative hypothesis, H1. And so that will mean that we are assuming not a mean of mu 0, but a mean of mu hat, okay, which is our maximum likelihood estimate. And we can have a look at what this likelihood is. So that is, again, a very small value. And now we can also do the same thing for the log likelihood, just as before. So here was the code line. I'll change this to H1, and here also I will specify that we want mu hat to be our parameter value. And we can have a look at the log likelihood for the alternative as well. And again, as a sanity check, we can see if this is equal to just taking the log of the already computed likelihood, which it obviously should be. So log of L H1, capital L, that is the same, right? So now we have computed the likelihood for both of these hypotheses, both like in the raw scale and in the log transformed version, like the log likelihoods. On the log scale, it is a bit easier to compare how big these likelihood, or actually log likelihood values are, right? So we see that this is a negative value, so minus 13.31 for the null hypothesis. And for the alternative hypothesis, we see it's very similar, but only slightly bigger. Like obviously it will be bigger because this is based on the maximum likelihood estimate, the one with, well, maximum likelihood. But we see it's like minus 13.28. So negative, that's why having 2.8 here as opposed to 3.1 means that this value is bigger than this one, right? We are on the negative side of numbers. And we can already see here where this is going, like this is only a very tiny difference. So in the next step, we're going to apply a likelihood ratio test to see if this difference is big enough to warrant rejecting the null hypothesis. I'm not giving away any spoilers or something, but just by looking at how small the difference is on the log likelihood scale, we might expect that there will most likely be a null result in the sense that the p-value will be very big and then we can't reject the null hypothesis, which should be good news because, well, the null hypothesis is true in this case because we know where these data came from, namely from a standard normal with mean equals to 0. So now, in order to conduct a likelihood ratio test, which is our goal here, we need to compute our test statistic, which in this case is this -2 times the log likelihood ratio. And I might just give it a variable name quite sloppily as -2 ln lambda, okay, just mimicking how this is written here, notation-wise. And this will be now equal to what exactly? Well, we have the information here, so it should be -2, of course, -2 times the log likelihood ratio under the null hypothesis minus the log likelihood ratio under the alternative, okay? We can evaluate this, and we see that our -2 ln lambda is in fact equal to this number here, 0.0556 and so on, okay? So as a next step, we want to see where this particular value, which again, under the assumption that the null hypothesis is true, should look like a value sampled from a chi-square distribution with the k parameter of the chi-square distribution set at 1. And you have to imagine that a chi-square distribution with this k, or sometimes degrees of freedom parameter, set to 1 looks roughly like this. So let me just draw a small picture here. This might be the probability density of the chi-square distribution, and this is like a specific value. And under the assumption that k is equal to 1, this distribution, actually it will start kind of at infinity, but it will go steeply down like this, and then it will continue like that. So that's a probability density function defined between 0 and positive infinity. And our value, which we are getting, like this -2 ln lambda value, the -2 times the log likelihood ratio, that is basically somewhere on this chi-squared scale, okay? And so it could be, for example, that our value is, let's say, here, if it is like on this scale, so it's maybe here. In that case, we take basically this as a cutoff, and then take all the probability area to the right, and the sum of this probability area will be our p-value. So if this is very large, like bigger than 0.05, then we would see that the likelihood ratio test gives a negative result. But we could also have maybe a very high value of this test statistic, for example, like very much to the right, let's say here, okay? If this was our value, then we would only take this area further to the right. And this might be small enough, like just intuitively looking, we don't have any real numbers here, but just intuitively, we might think, oh, like the further to the right this value is, the less probability area there's left next to it, to the right. So the p-value will be small, and we might see a significant effect. In order to compute a p-value for the likelihood ratio test, which is based on this chi-squared distribution, in R we have a function called p chi-sq, like p chi-squared, which works kind of just the same, with the same philosophy in mind as we already saw for p-norm or pt, okay? So this is a function that accesses the probability distribution, which is the chi-square distribution in this case, and we'll give it a particular value on this chi-square scale, in this case our -2 ln lambda value. And we also have to specify what is called df here, what we had called k here, like this parameter, which in our example, because just one parameter is held constant in the null hypothesis, will be just 1. So df, which is the second argument, will be 1, okay? And now as a result, this function will give us the area under the curve of this function. But by default, just as for the p-norm and the pt function, it always considers the area to the left of our value. But in this case, we want the area to the right, okay? Because that is actually the interesting area. If that gets smaller, then this will mean that the p-value is smaller. Like that's the way how we get the p-value, to compute the area to the right in the case of the chi-square distribution. So we will also have to add this argument lower tail equals false, which we already saw in previous examples, which will, right, as I said, make sure that we consider this area and not the one to the left, okay? So we can compute this, and that will be our p-value in this case, which you see is enormous. So if we would ask, for example, is this smaller than 0.05, asking is this a significant difference, as a result we would get false, okay? So here we have a very clear case, which is not surprising. We had a small sample of 10 data points. We already know, in fact, because we are like the gods of this universe where we simulate this data, okay, that the truth is actually known to us, namely the truth that these data are in fact from a generative process in which the null hypothesis is true. So it's a very good result that we find confirmation of that, namely in the form of a non-significant result, which tells us basically that there is no evidence indicating that we should reject the null hypothesis. So we basically found a true negative result here. All right, so as a last little sanity check, we can have a look at one thing, namely how we computed this -2 ln lambda test statistic here. So recall that what we had done here was to directly compute, well, -2 times the log likelihood based on the null hypothesis minus the log likelihood based on the alternative hypothesis in brackets. But as we had discussed earlier, there's actually a shortcut, an even simpler way to get this test statistic for this Gaussian like normal distribution case, which is to compute this particular mathematical term directly. So just as a kind of last sanity check that we get the same result using this shortcut way of computing the -2 ln lambda, let's just do it here quickly, which is to say, okay, we have something squared, and what do we square exactly? Well, it is mu hat divided by, sorry, not divided by, mu hat minus mu 0, but that should obviously also be in brackets now. And here we again have, sorry, oops. Yeah, so here we have the denominator, which is sigma. In our case, sigma was defined to be 1. So 1 divided by the square root of the sample size, which was 10 in our case, like we had generated 10 random data points. And evaluating this, as we see here, gives us exactly the same result as we had earlier when we had done it using this more general method, okay? So everything works out fine, everything makes sense. This is how you do a likelihood ratio test in principle for a Gaussian process model. All right, before we move on, there's one last notational detail I want to mention, which is that this fellow here, namely this -2 ln lambda test statistic for the likelihood ratio test, is also sometimes referred to as log LRT, okay? That's just a different name for it. And this refers to, so LRT obviously refers to likelihood ratio test, like likelihood ratio test statistic, probably in this case, and log because it's about the log likelihood ratio. So that's just an alternative way you'll see it referred to sometimes. So in the examples discussed so far regarding the likelihood ratio test, we have always applied it to the Gaussian process model, which is a quite simple model. And specifically, we have seen how to probe the mu parameter, the parameter for the mean using the likelihood ratio test. But I've mentioned initially that the likelihood ratio test is actually a quite flexible test that can also be applied to other statistical models and potentially even more complex models. And one other model we've already encountered and discussed so far is the simple linear regression model. Namely, as you remember, the model that says we have data y, which is modeled as alpha, the intercept, plus beta times another variable, x, and then there is some residual variation, okay? And here we also have two parameters, alpha and beta, and we can also apply the likelihood ratio test to, let's say, beta, which is actually usually the interesting question to ask. So if we have two variables, for example, the psychological symptoms and the stress level, we want to know if the relationship between those two that is modeled by the slope is significant. Another way to put this is to ask, is beta actually 0, which means that there is actually no interesting relation at all, or is it significantly different from 0? And that is also something we can find out, test basically, using the likelihood ratio test. So the likelihood ratio test applies to the simple linear regression model just as well as it applies to the Gaussian model, and as we will see later, to also more complex kinds of linear models. So in the next example of simulations in R, we are going to see how to use the likelihood ratio test on a simple linear regression. All right, so let's see how to do this in R. So for our simulation, let's say we have a variable x, okay, and that's our predictor variable, and let's say we have actually a very systematic sample of x in the sense that we have all the values from 1 to 10. Okay, so we can write this as 1 colon 10, which means that x has exactly these entries 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now again we are like creating a small little universe in which some sort of linear relationship is true because we are defining it, but then our test has to recover that truth basically. So we're saying that y, which is our dependent variable here, in our fictional simulation universe is dependent on x in the following way. So it is defined by some intercept alpha, where we could say alpha might be, well, it might be 10 maybe. Again, if it helps to think of an example, we can again think about the psychological stress and psychological symptoms variables, but any kind of linear relationship between continuous variables could be imagined here. Okay, so let's say the slope alpha is 10 in this case, and as the formula says here, that's then plus the slope times x. So we could say the slope maybe 20, so 20 times x, and then plus, well, what is given here is epsilon, which is just residual noise, not captured by this relationship. And how do we generate random noise? Well, we can just generate normally distributed data. Okay, so we could say we want R norm to generate 10 like random data points that will be added to this equation with a standard deviation of 10 and a mean of 0. Okay, so let's generate this y. We can see what y is. So y has these particular values, which means like the data point where x was 1 corresponds to y of 21, then the data point where x was 2 corresponds to a 51, and so on. Okay, so these are my predictor data, and these are the data from the dependent variable. And the key is now to understand how we can apply the likelihood ratio test to see if this slope is really different from 0. Well, I mean, we know as the gods of the simulation that it is in fact different from 0. It is 20, but in real life we don't create the data ourselves, but the data come to us and we don't know the process behind them. So the idea is you have to now imagine again that we are just receiving this data set in the mail, okay, and we just know that these are the y values and these are the x values, and we don't know how they were created. And now we have to check if the slope is really meaningfully different from 0 or not. So here's how to do this. We can first define the model under the null hypothesis, which is basically saying that beta is equal to 0. Okay, that's the null hypothesis. And we can do this using the LM function, which we've already used before in order to run a simple linear regression. And we want to say that is with a dependent variable y, and as a predictor under the null hypothesis there is no slope x. Okay, the only thing that is being estimated is an intercept. So the way to write this with the LM function is to write y tilde and then 1. If I just write a 1 and not a variable, that means that we are just predicting an intercept. We're just like estimating an intercept, but no slope, because the slope is constrained to 0, you can imagine. Like beta is set to equal 0. That's what this says. So we define this. This is our model M0. We can look at it. Well, it tells us that the data have an intercept of 120 according to the model. That should just be equal to the sample mean, by the way. But there is no estimate of the slope because the slope is constrained to 0 under the null hypothesis. Now there's a very useful function in R built in by default, which is the log like function, which is a function to compute the log likelihood of a model object. So for example, of a linear model in this case. So we can give this log likelihood function our model M0, which was the variable name we had defined for it. And now there is one small caveat. We'll have to do these kinds of brackets and then 1, because that's an object that contains multiple values, but the actual value for the log likelihood will be in the first cell. So that's why we'll have to index this as follows. And then we press enter. And now this is the log likelihood, like basically this value here for our model under the assumption that the null hypothesis is correct. Okay. Now let's also fit the alternative model. The alternative model, we can call it M1, will say that, well, there is a linear relationship again, where y is the dependent variable, but now we are allowed not only to think of the intercept alpha, but also of the slope, which is related to this predictor variable x. Okay, so we could write it like this. A shorthand for this, which is exactly equivalent, is to just write y tilde x without the 1 plus. That is, like, if we write this, this also implicitly means we are estimating an intercept. That's exactly the same thing. Okay, but just to make it really clear to ourselves that here we are estimating both an intercept, which can vary, and a slope beta, we can write it as given here. And we can press enter. Now our model 1 is fitted. As we see here, this model now predicts an intercept of 6.7 something and a slope beta for this predictor x of 20.9 based on our sample. And just as we did for the null hypothesis model, we can also compute the log likelihood for this model. So let's say we can write log likelihood, like log like in short, in R of M1, and then again we index it as follows with a 1, and we compute this, and we see that the log likelihood here is minus 36.07, so quite much larger than this one. Again, remember we are in the negative with a negative sign here, so a number that has a smaller absolute value is like larger, right? So this is minus 36 is larger than minus 55. Now, as we know from here, we can compute the log LRT test statistic, so the -2 times the log likelihood ratio, as follows. We can do -2 times, and now in brackets we have this subtraction, so the log likelihood from model 0 minus the log likelihood from model 1. And so this, maybe let's save it in a variable called log LRT, right? This will be our test statistic, which under the null hypothesis should be approximately sampled from such a chi-square distribution, okay? So let's see what this actually is. So in this case, our test statistic is equal to 38, okay? So on this scale of the chi-square distribution with degrees of freedom 1, if we find the 38 and then we look what's the probability area to the right of it under the curve, that will be our p-value, okay? So that's what we can do now. We can again use the p chi-squared function that we already saw. We will give it as its first argument the observed sort of chi-squared value that we have here. And then the second argument is the degrees of freedom, or this so-called k parameter, which again, because we are just holding one parameter constant in the null hypothesis, namely beta, is again just 1, okay? So we give it that. And then we press enter. Oh, okay, one small thing is, of course, we have to do lower tail equals false. So here we see the correct result. So this is now the area to the right of it under the curve, which is a very, very tiny value, like it's almost 0, okay? In such a way, almost 0, that actually when we did it the other way around, where we computed the area to the left of it, it basically approximated it to 1. Like it's almost 100% of the probability area are to the left of this point. Okay, and that's why the result is 1 here, or if we do it the correct way to actually get our p-value, which is the area to the right, we get a value which is basically 0. Like it's somewhere in the order of magnitude of 10 to the power of minus 10, so very small, practically zero. Okay, obviously not exactly zero because there's always more area to the right for a finite chi-squared value. But anyway, so this is our p-value here. So here, sorry, and if we want to think about it as a hypothesis test with some significance threshold, we could again say, is this p-value smaller than 0.05? Well, obviously it is. So in this case, we get a significant result, which, as we know, because we were in control of this simulated data generation process, is a true positive, because we correctly conclude here that we should reject the null hypothesis, that the slope is zero, and should in fact accept the alternative hypothesis, which is that the slope is not zero. In this case, the alternative indicates that the slope is, well, the maximum likelihood estimate is 20.97, which is already pretty close to our real slope that we defined when we created this data, which was 20. So going from 20 to 20.9, that's very close to the true parameter value. So that's a very good estimate right here. Lastly, just as a reminder, another way to think about this hypothesis test, which is equivalent to the way where we compute the p-value, is to think about what is the threshold value on the chi-square scale after which the result is significant. So we are basically asking which is the critical chi-square value at which, when we stop at it and then we measure the area to the right, we will have exactly 5% of the probability area, which is our significant threshold. Or to the left of it, we would have 95%. And so we can compute this critical chi-square value using the q chi-square function, which is the one that gives us the quantiles, and we give it as input a certain probability. And so here we want to do, let's say we want to find the value at which, to the left of it, there are 95% of the probability area. So we will say 0.95. And again, for the function with degree of freedom 1, so again we have to specify this 1, just as we did here for the p chi-squared function. And we can see what this is actually. So this is 3.84. In other words, already at the point where chi-squared would have been 3.8 and or greater, we would already find a significant result. And here our observed chi-squared value, or actually the log likelihood ratio test statistic, but it's basically a chi-squared value, was even 38.4 something, okay? So that's huge. That's almost 10 times as big as our critical chi-squared value. So it's no surprise really that the test comes out significant. All right, so we've seen the likelihood ratio test both on the Gaussian process model for one continuous variable and its mean, and we've also seen it for the simple linear regression model and the slope parameter in particular. But we can always go higher, right? And if you remember, towards the end of statistical data analysis 1, we encountered more complex kind of linear model, namely the so-called linear mixed effects model, okay? So the linear mixed effects model, just as a brief recap, is an extension of the simple linear model with the idea that it can model hierarchical data, okay? For example, the data that come from a repeated measures experiments in psycholinguistics, where we have both different participants and different items, and per participant we have multiple measures, okay? So the data are kind of hierarchically structured like this. If you just pick one data point, you can't just say that it's identically and independently distributed with any other data point, because there are certain subgroups of data points. For example, the subgroup of all data points belonging to subject number 1, or the subgroup of data points belonging to item number 3, okay? And that's this hierarchical structure of the data that a linear mixed effects model can account for. Now let's remember how it is mathematically defined. So the basic structure is of course similar to the simple linear regression model, at least if we assume a kind of simple mixed effects model with like one predictor variable and one intercept, then we could write it as follows. I'll make like some small adjustments. So the residuals don't go away, but I'll have to write them again a bit further below. So the most obvious thing we will notice is that now there are two indices. So before we had an index I, which was like the subject, the participant, but now we have both subjects and items. So we might say I is the index for a particular subject, and then J right next to it is the index for a particular item. And then here we have I and J again for this predictor variable data. And in fact, let me just rebrand the parameters alpha and beta slightly differently. You will see right now this is actually quite useful. So there's just a renaming. It doesn't really affect what they mean, but okay, I will call what I called beta before, I will call it beta 1. Okay, that's the slope. And what I called alpha before, I will call beta 0. Okay, you'll see in a moment why that's quite nice now, because this is like what we see here is just the so-called fixed effects of the model. So the overall intercept and the overall slope that the model has to estimate. But then in addition to that, and that's the crucial extension that the linear mixed effects model provides, we also have by subject and by item adjustments to the intercept and the slope, the so-called random effect structure, okay? And we would write this down as follows. So we could write this, okay? But plus U0I plus U1I times our predictor X ij, okay? This is the so-called subject level adjustments. And then we also have something similar for items. So we could write plus W, which is now conventionally we can use W for the items and U for the subjects, but it's really just an arbitrary decision, okay? So W, U, J plus W1J times our predictor variable X. That is for the by item adjustments. So here, just to explain this, for example, U0I is the adjustment by subjects for the intercept, whereas U1I is the adjustment by subject for the slope. Okay, so now you see maybe why I've called my intercept and slope beta 0 and beta 1 now, because now using this 0 and 1 distinction, we can keep track of if something refers to the intercept 0 or to the slope 1 here, okay? And the usefulness of this is basically the consideration that in this kind of hierarchical data, there might be some individual differences, like maybe some subjects have like show a very strong effect of this predictor. So then the adjustment to the slope that's like computed or estimated individually for each subject will take care of accounting for that variance. And likewise for items. And you know, these adjustments happen both to the item, to the intercept and to the slope, at least in this maximal random effect structure that we are assuming here. And of course, there is also, just as for the simple linear regression model, this residual term, which is just like, you can think of it like random noise, random variance that is not explained by our intercept and slope of the predictor here. And that is assumed to be coming from a normal distribution. So this noise, the epsilon, is actually generated from a normal distribution. I'm writing n now as a shorthand for normal with mean 0 and a standard deviation of sigma, which is our population standard deviation, okay? Now, regarding the random effect structure, we also need to specify something else, namely how its variation comes about, like how much the by subject and by item adjustments vary, okay? And this is specified by the so-called variance-covariance matrix. And we have one such matrix for subjects and one for items. So the way this is defined is as follows. We usually write capital sigma for the variance-covariance matrix, and then we write U for subjects in our case. And this matrix is a 2x2 matrix, so it has 4 cells, like 2 rows and 2 columns. And its content is as follows. So in the upper left corner, we have sigma U0 squared, which is basically the variance by subject of the by subject adjustments for the intercept, okay? And likewise in the lower right corner, we have sigma U1 squared, which is the variance of the by subject adjustments for the slope, right? And now in the remaining 2 cells, we have the following term. We have rho, which is like not rows and columns row, but like the Greek letter rho, rho U times sigma U0 times sigma U1, okay? And the same term actually is also in the remaining cell of the matrix, so rho U times sigma U0 times sigma U1. That is the content of the variance-covariance matrix for the subject level random effects. Now this rho parameter here actually quantifies the degree of correlation between the by subject intercepts and the by subject slopes. So that's just something that this takes care of. Like if there is a huge correlation between the random intercepts and the random slopes, this will be captured by this rho U parameter. And just as there is a variance-covariance matrix for subjects, there's also an analogous one for items, which looks very much the same, just with W instead of U here. So let me just put it here quickly in the interest of time. So that is our by item variance-covariance matrix. Looks very similar, right? And so the linking missing piece between these matrices and what we have specified here, like the U's and the W's, like the adjustments for either intercepts or slopes, is the following. So we are assuming in this model that for example, let's start with subjects, that the by subject adjustment for the intercept for some specific subject I, okay, indexed with the letter I, and the adjustment for the slope are coming together like as a vector from a multivariate normal distribution whose variance is described by this variance-covariance matrix. So to put this mathematically, we could write the vector which contains the adjustment for the intercept and for the slope by subject. So U0i and U1i. That's just a vector containing these two, and like it says, these two are conjointly generated from a multivariate normal distribution. So we could write n again for normal, or in this case multivariate normal distribution, and this multivariate normal takes as its mean also a vector of length 2, namely a vector containing 0 and 0, okay? And as its variance specification, we will now give this multivariate normal distribution function our variance-covariance matrix for the subjects. So our sigma, capital sigma U, basically. And so what this is saying is that like the adjustments by subjects are coming from a multivariate normal with these like sigma U0 and sigma U1 as variances, but it also takes care of thanks to this correlation parameter, of the possible correlatedness between these two. So that's the specification for the subjects, and the same thing we can also do for items. So here it comes. So here is the analogous specification for the by item random adjustments. Now, this is the full specification of this linear mixed effects model. As you just witnessed, it takes a little bit more time to write it down properly than for the simpler models we saw earlier. But once we have everything spelled out, it's pretty clear mathematically what it does. And now coming back to our actual topic, the likelihood ratio test, the beauty of this likelihood ratio test is that it can handle even such a monstrosity like this linear mixed effects model in just the same way as we saw for the simpler models. And the idea is, again, we basically pick out any Greek letter here because that's how we denote parameters. So everything here that has a Greek letter, like beta, okay, maybe not the epsilon, but like the beta 0, beta 1, the sigma U0, or the population level sigma, or the rho U or the rho W, this correlation parameter. All of these are parameters that we can estimate, right? And all of these are also parameters that we can run hypothesis tests on by saying, okay, is it like meaningfully improving the likelihood of my model if I don't constrain a certain parameter to 0, just like we did before for the mu of the Gaussian process model or for the slope of the simple linear regression model. In just the same way, we could constrain the slope here to 0 in the null hypothesis and say, okay, do I get a significantly better likelihood if I don't constrain it? But we could do it for any parameter that we see here. We could also, for example, pick the correlation parameter rho u, which describes the possible correlation of the bi-subject slope adjustments and the bi-subject intercept adjustments. And we can ask the same question. We can say, okay, our null hypothesis is that rho u is 0, and our alternative is that there is a correlation between the bi-subject intercept and the bi-subject slope adjustments. And just in the same way, we can run a likelihood ratio test to basically quantify the degree to which such an alternative hypothesis would be warranted. So this likelihood ratio test is also a great way to do model selection. So often with more complex models, there is no obvious way how many parameters you should assume to vary freely, and often you'll also run into convergence problems in practice if you try to fit completely unconstrained models on like small data sets. So often there is a question, okay, can we simplify this model? Sometimes you would run a linear mixed effects model that doesn't include these correlations or like restrains them to 0, basically sets rho to 0, or a linear mixed effects model that only contains intercept adjustments but no slope adjustments. And so to make like properly informed decisions about which parameters we can drop without losing too much explanatory power, a great way is to compare two nested models. For example, a model that doesn't constrain a particular parameter versus a model that does constrain it, and then see if the likelihood ratio test comparing these two models tells us that there is a significant result. And if there is, then probably including this parameter is actually quite useful because it does explain significantly more variance in our data. All right, so in order for you to believe me that this is actually possible, we might want to see a real-world example, actually, no simulated data, actual real data, namely data from a psycholinguistic experiment from a study by Grodner and Gibson, 2005, in which the authors ran an experiment comparing the processing of subject and object relative clauses. And the dependent variable here are reading times, okay? So that's what we're going to look at now. So let's open RStudio. In order to use this data set, we'll have to first, if we haven't done this already, install the package devtools. This will take a little moment, but once this is done, we can use this DevTools package in order to install the custom R package linksike, which is the R package attached to the book which is accompanying this lecture, like the frequentist Statistics for Cognitive Scientists book by Professor Vasisht. And the way to do this is to write DevTools ;:, and now install _GitHub. And inside this we do quotation marks and Vasisht / and then linksike. Okay, this will install the linksike package, which contains this dataset I just mentioned, the Grodner and Gibson 2005 dataset. So this also will take a little moment, but you will only have to do this once. Once you've done this once on your machine, this package will be available to you. Oh, I have to specify something here. I don't want to update anything. Okay, never mind. All right, so the installation is done. I can now load the linksike package just as I would for any other kind of R package. And now to access the particular dataset by Grodner and Gibson 2005, I can write data and then df gg05e1, like Grodner and Gibson 2005 experiment 1. And now this will be saved automatically in a variable called df _gg05e1. To simplify a little bit, I can also call this just gg05e1. Okay, so now this is my data set. It's a data frame. I can see what the first couple of entries are using the head function. So head of gg05e1. And this is the structure of the data. So I see there are subject indices, like there is, for example, all these couple of observations right in the beginning all pertain to subject number 1. There are different items, so exactly this kind of hierarchical structure of a repeated measures experiment that we are seeing here. So different kind of items and also different kind of subjects, and for each subject we have multiple measures, and likewise for each item, because again, subject 2 will see the same items, right? And there are 2 conditions. So this is our predictor here. It's a categorical variable, but it's just the same. We can just code it as a numerical variable, as we'll see in a moment. And so the 2 levels of this categorical predictor are object gap and subject gap, like basically the object extracted versus the subject extracted relative clauses. And here, this is our dependent variable. The raw RT, the raw reading time in milliseconds, is a classical continuous DV. Okay, so we can run a simple linear model on this. So now let's recode our predictor here as numbers. So we'll apply contrast coding, in this case sum coding, which will be, given that our data is balanced, we can code one of the levels of the 2 levels as positive 0.5 and the other one as negative 0.5, right? And then we can use it basically in such a mathematical formula. So we'll do this. We can create a new column in this data set. So we'll write GGO5E1 and then $, and now we'll create a new column, which we may call SO, like subject, object, relatives, okay? And here we'll say, okay, this column should contain the following values, namely if the value of the column condition is equal to object gap, in that case, it should have the value 0.5, okay, 0.5. But if it isn't, meaning that it is actually pertaining to the condition subject gap, then it should have the value minus 0.5, okay? So we can run head on this data set again to see that this column is registered, and indeed we see now there is like a new column SO, which is just the same content as that one, but coded as 0.5 and minus 0.5. Now we can use it as a predictor, basically. Right, so let's do this. We can load the library LME4, which you've surely encountered also towards the end of Stats 1, like last semester's course, which is a standard R library in order to run these kinds of linear mixed effects models. And now comes the crucial idea. So we will define our model under the null hypothesis. And what is our null hypothesis? Okay, we have to pick some parameter that we want to test, okay? So the most obvious and usually most interesting kind of parameter we might want to consider, especially for this kind of hypothesis in this experiment, is the general overall slope, okay? So that's always the hot one. That's basically describing if there is an overall relationship which is non-zero between our predictor, in this case, if a relative clause is a subject or an object extracted one, and our dependent variable, in this case, the raw reading time in milliseconds, all right? So our likelihood ratio test will now basically compare two models. One model which constrains this predictor to 0. It will still have, that's the interesting thing, it will still have the subject and item level adjustments for the slope. So that we don't remove that as well. But we will constrain the model to only such situations where this overall slope is equal to 0. So you can imagine this term disappearing, basically, or you can imagine a 0 here instead of this beta 1. That's effectively the same thing. So this is our null model, okay? So how to write this in the LME4 syntax? We will have to write LMER for linear mixed effects regression. Now, we will also want to model our dependent variable here, the reading times. But actually, okay, there is a small adjustment here. If you're a good psycholinguist, you know that reading times or reaction times are usually not normally distributed, but we can transform them into a normally distributed variable, roughly speaking at least, by taking the log of them. So often we actually model log reading times in log milliseconds as opposed to raw reading times in milliseconds. And that's a good practice, also helps with possible distortions by outliers. So let's do that here. So we will just write log of the raw RT will be our actual dependent variable here. And then we will have the tilde sign, and now we specify the model formula. So the model formula first says, okay, there is an intercept, so that's a 1 in LMER syntax, and then there's also random effects. So the random effects in this case may be the by-subject effects, okay? So I will write 1 plus SO, both intercept and slope, by subject. And then there will also be by item effects. So, sorry, 1 plus SO by item. Okay, notice here, by the way, I could also have used the single vertical bars here. That's maybe something you might be more familiar with. I'm using the double vertical bars, which, as you may remember, is shorthand notation in this LMER syntax to say that the correlation parameters are rho U and rho W are constrained to 0. So we're assuming that there's no correlation between the by subjects intercept adjustments and the by subject slope adjustments, and likewise for items. So we're doing this, otherwise the model might be too complex and we might run into convergence issues here. So just for the sake of this example, I will constrain this to 0, and so this is obviously the same, and this to 0 as well, okay? That's what the double colons do. Now, having specified this, we are basically good to go. There's just one minor thing which we will have to do when we compute linear mixed effects models with the goal of running a likelihood ratio test, namely that we have to specify this argument in caps REML to be equal to false. The details of this are a bit technical, but the idea is that this is restricted maximum likelihood estimation, which is not really computing the overall full likelihood as we need it here to do the likelihood ratio test. This has benefits in other cases, but in our case, where we specifically want to compare two models with a likelihood ratio test, it is actually distorting the results. So here we have to really set the REML to false in order to be able to then compare two nested models. Oh, right, and one crucial thing we shouldn't forget is to actually provide this LMER function as a second argument, the data that we want to examine. So in this case, the data set, what was its name again? GG05E1, right? Otherwise, obviously, we can't run the model if the LMAR doesn't know which data set to run it on. So we're basically ready to fit our linear mixed effects model now. All we have to do is press enter, and then it's fitted. Likewise, we will now specify the model that represents our alternative hypothesis. This we may call M1, okay? And here the only but crucial difference is that we are not constraining this slope parameter beta 1 anymore. So here we had basically constrained it to 0 in the null hypothesis model, but now we are saying no, there is actually possibly a non-zero slope overall, okay? So we will now add SO as a predictor, which is basically representing our slope now. And we will run this model as well. That also was very quick. And now we can do the following. Now we can use the ANOVA function, which is also from this LME4 package, which among other things can be used in order to compare two such fitted models using the likelihood ratio test. Okay, so we are not seeing the technical details now as much as we did in the previous simpler examples, but under the hood it does very much the same thing conceptually as we also saw previously. And now the thing we have to do is to specify the model objects in which our two models that we want to compare are stored in, so M0 and M1 in this case, and we can run this code, this line of code, and see what comes out of it. So this is the output. I'm gonna make this a little bit bigger so we can see it a bit better. So here's the interesting part of the output. As we see here, like M0 and M1 refer to our two models, the null hypothesis one and the alternative one. And we have different kinds of information here. Most relevantly, okay, here you can see n power, which specifies the number of parameters that each model has. So the null hypothesis model has 6 parameters, and the alternative model has 7, because it also has this one, this beta one, so one more parameter. And here you can see the log likelihood computed for each of these models, right? So for the M0 model, it's minus 350 in log likelihood. For the M1 model, it's minus 347, right? And this chi-squared statistic, which is basically minus 2 times the log likelihood ratio, that is computed here to be 6.1235 something, okay? The degrees of freedom are 1, again, because we have one parameter that's constrained in the null hypothesis model compared to the alternative. So again, we will have to look up this value in the chi-square distribution with the k, or degrees of freedom parameter, set to 1. And when we do this, we get the following p-value. So here in this output, we also directly get this p-value, which is equal to 0.01334. And this p-value apparently is smaller than 0.05. That's why it gets this star annotation here, because here star means it like passes this significance threshold of being at least smaller than 0.05, for example. So if we had this threshold of 0.05, the conventional one, then we would conclude here that the result is significant, meaning that indeed whether we have subject or object relative clauses makes a significant difference on the reading times. If we want to confirm that this p-value does indeed correspond to this test statistic, we can also compute the p-value ourselves, right? So we can do, again, p chi-squared of this value here. So I'll just copy this with the degrees of freedom set to 1, and lower tail again specified as false. And when we run this, we see here as well, the 0.01334 p-value that we also see in the output here. All right, so we've seen the likelihood ratio test applied on the linear mixed effects model, specifically for how to probe this slope right here. And here we have the conclusion indeed that the slope is relevant. It significantly accounts for variance in the data. Okay, there is one last example I want to show you guys of how to apply the likelihood ratio test on a linear mixed effects model. Now, let's maybe consider a different parameter, right? So maybe let's see again what our M1 model was. Let's take this now as our baseline, as our null hypothesis model. And just looking over here, what kind of parameter have we until now constrained to 0, but which could potentially also vary if we leave it unconstrained? Well, I've marked this here. So either the correlation parameter for the by subject random effects or the one for the by item random effects. Let's maybe pick the one for the subjects and say, now we want to not constrain it to 0 a priori, but we want to actually run a hypothesis test on whether this parameter should be 0 or not. Okay, so now we're treating it basically in kind of the same way we treated the slope in what we just did. So now this RU, which appears here in the variance covariance matrix and also down below here, this is now our parameter of interest, where we want to check if including it in the model leads to a significant increase in explained variance or not, right? So M1 now is our null hypothesis model. And so let's analogously define a new model, which is M2, with the only difference that now we allow this correlation parameter to be estimated. We don't fix it to 0 as we did before, which is represented by this double vertical bar, but we actually let it be estimated, okay? And we can fit this M2 model. And now, just as we did before, we run the ANOVA function, compare our two models. So now our null hypothesis constrains this parameter to 0, but our alternative says, no, this parameter could also be estimated, like there might be a real correlation between the by subject intercept and the by subject slope adjustments. And we can run this ANOVA. And again, we get similar kind of outputs. So we have the log likelihoods, which are estimated for each of these two models. And we also have the chi-squared statistic, basically the -2 times the log likelihood ratio. And again, we have the corresponding p-value, which also suggests here that it is actually worth including this correlation parameter, because indeed it does explain a significant amount of additional variance. So I hope these demonstrations of the likelihood ratio test on well, either simulated or real-world data and different kinds of models, like of varying complexity, applied to different kinds of parameters, have convinced you just how flexible and useful this general framework of likelihood ratio testing is, because we can now do hypothesis tests on basically any kind of parameter we can think of in the kinds of models that we have encountered so far. That's it for now. So in this lecture, we have revisited the idea of what model parameters are and why at the core of statistics basically lies the idea that we want to estimate the values of parameters in the models that we suppose. And we also talked about what a likelihood is, or a log likelihood for that matter, and how we can compute the so-called likelihood ratio, which is the basis for the likelihood ratio test, a very flexible and generalizable kind of hypothesis testing framework designed for basically testing hypotheses about virtually any kind of parameter in a frequentist statistical model. We also saw a couple of examples of the likelihood ratio test in action, whether that be on a simple Gaussian process model, where we wanted to basically test whether the mean is or not equal to 0, for example, or we saw how it's applied to a simple linear regression model, where we want to see if there is a meaningful, significant relationship between two continuous variables, like the predictor and the dependent variable. And lastly, we saw the same idea, but in the much more complex and powerful framework of linear mixed effects models, where we also had one likelihood ratio test applied to the slope of this model, the general slope overall, not the random effect one, but the specific fixed effect slope. And lastly, we also saw that we can also do the same kind of test on other parameters of the linear mixed effects model. For example, the correlation parameters for either subjects or items. So that's the content for now. Some of it I know is kind of repetition from Stats 1, but I think it's really good to revise a few of these concepts a bit further to really be sure that we're all on the same page. In the next lecture, we are going to talk about matrices, kind of in general. So for those of you who don't really have a lot of experience of computing, like calculating with matrices, this will be a good opportunity to catch up. And this will be important in order to then be able to talk about the so-called matrix formulation of the linear model, and then in general to move on a bit further into the advanced topics of linear modeling theory and also generalized linear modeling theory, as we will then encounter. So that's everything for now. Have a lovely week and see you next time.